So soil health is a term often used and at first defined by consideration of production. We consider a productive pasture to be a healthy pasture in terms of the forage generated and the animal weight gains from that forage. But how about if I held a few grams of soil in my hand? What could I measure on that soil to determine is the soil healthy or not? What measurement could I make on the soil directly? That's the question I've been looking at with the Brookdale study. Here we are for these presentations at Brookdale. And the study encompasses a comparison of two types of pasture management. We have the continuous grazing, where the cattle are put out on the field for the season. And then the planned grazing, where we have cattle moved in paddocks at a density of 25 cow-calf pairs per acre per day, approximately. In this way, then, with planned grazing, there's no opportunity for selective grazing by the cattle, so they cannot overgraze their favorite palatable species, leading possibly to the degradation of the pasture. And also in the planned grazing, we have a long rest time between grazing events to allow the forage to grow well. So we're anticipating that planned grazing should provide a regeneration of good pasture and possibly increased soil health. So when we consider soil health, we might address the issue of microbes in the soil. That would be bacteria and fungi. Then microbes would be contributing to soil health through their function. For example, we have the bacteria that are contributing to nutrient availability through mineralization of nitrogen, for example. And then we have fungi that would be contributing to uptake of nutrients by the forage through mycorrhiza. Okay, so we have microbes there. So if I could measure microbes on the soil, would that be a measure of soil health? And our starting place is to consider the soil organic matter. We can measure organic matter. That may vary across the site, and we think that could be important in relation to the microbes. So let's take that as a starting place. Let's address the relationship between the microbes and the soil organic matter. We can measure the organic matter by a loss of weight of the soil on heating. After factoring the loss of moisture first, the further loss of mass on further heating will be from the loss of the organic matter. And we can convert that to carbon. There's a straightforward relationship to convert the units from organic matter percent to soil organic carbon instead. And we can relate that to the quantity of microbes. We have a method to measure the quantity of microbes in the soil. And when we do this, we find that there is a straight forward relationship, a linear positive relationship between on the x-axis we have the soil organic carbon or organic matter, and then on the y-axis the quantity of microbes. And then we find that as our organic matter goes up, so does our quantity of microbes. Similarly, we can look at the functional performance or activity of the microbes in terms of respiration. There's a measure we can take of the so-called burst respiration. We can dry the soil and then re-wet it, and then we find that there's a release of carbon dioxide in response to that drying wetting cycle, and that is a measure of activity of the microbes. So we can relate that also to the organic matter, and once again we find there's a positive linear relationship. The more organic matter or soil organic carbon, the more respiration in the burst test. So we've got here a good, reliable driver, as it were, a driver variable, which is soil organic matter, the amount of soil organic carbon there, talking particularly here about the top 6 inches of soil, the top 15 centimeters, that's driving the microbe quantity and the microbe activity in terms of carbon dioxide release from the soil. So how does this relate to the pastures? Well, the study here at Brookdale, we've got 7 different areas across the site. And in each area, we have a continuous subdivision, and then we have a planned area of forage. So we've got this repeated to make 14 areas, so experimental units, as it were, across the site. And over a handful of years, quite literally, I think 6 years, we've been measuring the the organic matter in these soils. And we've been looking periodically. We've looked at the quantity of the microbes and the activity of the microbes through these measurements. And in summary, for that set of data, we find that the Brookdale site is fairly high in organic matter to begin with. It's up in the range of the order of 8 or 10% organic matter. That is fairly high. And then we find that we have this relationship for both the microbes quantity and activity. But when we compare the two different types of pastures, we see no difference emerging over the handful of years of the study. There seems to have been no loss of organic matter thus far in the continuous grazing. Although we do see changes to the vegetation composition, we do see greater abundance of weedy species. Thistles, for example, where and various other weedy species, we can see these increasing in quantity, where the palatable species having been overgrazed in the continuous. So we can see differences in the forage composition in the continuous compared to the planned, and that may have impacts for the producer. But we don't see over this time period a loss of organic matter from the two grazing systems. So if that's our measure of soil health, and we think we're on the right track there, then it doesn't seem to be a degradation of the organic matter over this time frame. However, if we were to go to a cultivated system, a cropped system, then we'd expect there to be quite a significant loss of organic matter. We may drop down from 8 or 10% down to perhaps 5 or 7% organic matter through years of cropping, perhaps. Now, in that kind of situation, we may regenerate organic matter faster, perhaps, in a planned grazing compared to a continuous grazing. Maybe that's not been tested here in this study at Brookdale. We started off with a pasture and we end with a pasture, but that may be the case. There may be a role for regenerative agriculture to use planned grazing to enhance organic matter accumulation. Maybe that, although not demonstrated here in the Brookdale study, maybe that occurs elsewhere. I'm not saying that doesn't happen, but at least at Brookdale here we have no impact, no degradation of the organic matter from the two grazing systems. That's my summary there for soil health. Moving on. Now, farmers are very interested in the quantity of carbon in the field. Let's look at the landscape and say, well, how many tons of carbon do I have in an acre or a hectare? That's my carbon inventory, and that may relate to management or to financial compensation. Okay, so we want to know how much is the carbon stock. And in this case, we'll be looking deeper than the top 15 centimeters. We want to look beyond the concentration of the most of the roots go deeper than 15 centimeters, but most of the roots are at the surface. We need to look deeper than that because we think there'll be carbon at greater depth. So sampling here is to 1 meter, 100 centimeter core. And of course, we need a power system to drive the core into the ground to that depth of soil. And then we can break it up into intervals 0 to 15, 15 to 30, 30 to 60, 60 to 100. And for each interval, we can determine how much organic matter is there. And as long as we know the bulk density, that is the mass over volume for the soil core, then we can calculate the carbon stock, how much is in the field at each depth interval, and sum them up to be able to calculate the quantity of carbon in the whole field. Okay, so that was undertaken here at Brookdale, but also across a number of farms across the province of Manitoba. And I can summarize those results too. Well, this was more of a methodological question, how to do and how to address challenges. 3 challenges came up immediately with this deep soil coring. The first is the soil core can be compacted. When you measure the depth of the hole and the length of the core, typically the length of the core is less than the depth of the hole. The soil has been compacted by the taking of the core. How do we overcome that? Well, we can't with a deep coring system. We could take a shallow core with specialized tools from soil physics to get no compaction, but we want to go deeper. We don't want to go to 15 centimeters. We want to go down a meter. So we've got to use a deep coring system with a hydraulic system to push it down. So we're stuck with this compaction. We could dig a soil pit, perhaps with a backhoe, and then go in horizontally to the profile face, and we'd avoid compaction that way. But that's not practical for many cores to be taken, and farmers may not like backhoes digging holes on their pastures anyway. So maybe we're stuck with this. We have to deal with this compaction issue. So how to deal with problem number 1? Well, what we've been doing is operationally, we've been monitoring the compaction and setting a limit on it to reject cores that are 10% compacted or greater. Typically, the cores that we collect, we're finding are of the order of 2 to 5% compaction. And so we're living with that. We monitor it. We know it's there. At least we know what it is. Problem number 2 has been that the core is sometimes difficult to extract from the metal sleeve of the coring device. And lubricant is used. There's some WD-40 perhaps, silicon base, to ensure the soil is going to come out of the core. Does that contain carbon? We think it does, of course. And then does that carbon contribute to the organic matter or the measurement of soil organic carbon, as it were? So to compare that against a check with no lubricant, we took a shallow core to 15 centimeters alongside the deep core, a handheld coring device, no lubricant used, and look at the organic matter in the shallow, no lubricant core to the shallow interval of the deep core and check that there's no difference. And indeed there isn't any difference. You get the same organic matter signal off the two. So it seems that we can successfully conclude that we don't have to worry about the lubricant. It doesn't seem to contaminate the core with carbon. And the third problem is that when you look at the cores, especially at depth, there are often stony materials, gravel at depth, especially down to that 30 to 60 centimeter layer or the 60 to 100 centimeter layer, plenty of gravel there in some cores. And of course that gravel or coarse fraction, the material that doesn't pass a 2 millimeter sieve, is not contributing any organic matter. It's just gravel. There's no organic matter in it. Yet that does contribute to the bulk density. So it came to me that we have to modify our calculation to use not the core bulk density in our calculation, but to use what is called the fine earth bulk density, where you calculate a bulk density that would be in place for that depth interval if there were to be no coarse fraction there. Just the density, the mass over the volume for the mass of the fine earth that passed a 2 millimeter sieve. Adjusting the calculation to take that into account will drop the carbon inventory for the field by about 10%. So that's worth doing and worth knowing about. And our summary for Brookdale at the site, this study was over a series of 42 deep cores. That's 3 for each of the 14 units, 7 replicates, 2